Okay, my friends, this is going to be a hoot for a Roger. The Nobel Prize Committee gave CERN the Nobel Prize for finding what they call was the Higgs boson. Now, I'm going to tell you right now, they do not understand the Higgs boson. I do. And here's what the Higgs boson is. Right here, these are Higgs bosons. And these are real Higgs bosons. Guess what they show for Higgs bosons right there? Yeah, that's their Higgs bosons. Now, our Higgs bosons were these actual Higgs bosons from field concussion and collision. They had head-on collision of gigantic particles. And I'm going to go through this very deeply, so this is going to take a while. So get us a little soda or something. Now, not only could we see the Higgs bosons, we could actually see the muons and the electron neutrinos. And here they are in photon phase, and here they are exactly what they say from, this is not my stuff, they say the neutrino, muon neutrino, electron neutrino, attached together are diracs. They separate, the muon turns just into a sterile black muon, the electron goes into shower mode, and this creates trillions of electron volts. We accelerated light. Get ready, hold on, I'm going to talk about Einstein first, and then just wait till you see what I have to show you. It changes everything, and we have to do it right away if we want to help to save this Earth. Okay, my friends, Roger once again. We're going to have outstandingly tons of fun today. And what are we going to have about the theory of light, gravity, weight, and all this stuff. You see this? The weight of nothing could mean everything to physics. This is SciShow. And listen to this now. Einstein, when he first published his papers, in his equations, he inadvertently predicted that the universe was contracting under the effect of gravity. That's what you would expect. Gravity pulls other things together. You would expect that. But he also said the speed of light is constant. And they could see the light was slowing down as it was coming to us, which had to mean that the planets were moving away, dragging that light away with them. We got a lightning storm going on right now. Now, they were dragging the light away. And that's why now they say it's expanding so fast, it's going faster than the speed of light. Just light is slowing down slower and slower, coming through all these fields. He was right the first time. It could be contracting. Now, I'm not saying it is, but it's certainly not expanding with the exponential amount of expansion they're talking about. That's insanity. All right, I'm going to let him explain what they're going to try to do to find the weight of nothing. Listen to this.
A Sardinian mine in the middle of the Mediterranean, physicists are building an elaborate experiment to find the weight of absolutely nothing. Now that might sound strange, but they're trying to get to the bottom of what's unofficially called the worst prediction in the history of physics. See, our universe is not only expanding, that expansion is also accelerating, and
this is totally wrong, this part. And if he buys into that, nothing's going to be correct here, but listen.
Scientists aren't really sure why. Because right now, theory and observation don't quite match up. And when I say quite, I mean one theory has predicted an expansion that's 10 to the 120th power too intense. So scientists need to weigh the vacuum of space to find out why our universe hasn't ripped itself apart yet, and which, if any, of our theories are to blame for the colossal mismatch.
Good idea. Let's take a look. All right, so they start looking for dark energy. Now listen to what he has to say.
This phenomenon, dark energy. And based on how fast distant galaxies were flying away, they calculated that dark energy must make up around 68% of all the stuff in the universe. But despite being so abundant, it's still not clear what dark energy is. And that's where the cosmological constant comes back into our story.
All right, the cosmological constant is the same as all these other nonsense constants, like the constant speed of light. It's not right at all. And a cosmological constant is another thing. You have to, and Einstein had to revamp everything to say, all right, if we just say this is always going to be constant, which it never will be, whatever it is, then my equations will work out. Well, they're not going to work out because the constant things are not constant. They're just things they made up to justify the numbers that they're writing down. And just like he said, observation and the theoretical numbers are so far off, it's just unbelievable. And it's because they have to follow Einstein's rule that light can't slow down. That's the only reason light's getting slower. It's getting slower as it comes to us. That's why it red shifts. Red shifting means it's slower and slower and slower. And the same thing with the microwave, cosmological microwave background. It's light that's so slow now that it's just barely moving. That's all it is. And they just can't understand that light can slow down, speed up. I could show it, and I will right now. All right, I just want you to know, light can speed up, light can slow down. I wrote papers on this for years, and in 3 of 2019, I published a paper, and this fellow here, Paul Amatucci, got a hold of me. He said, can I write books about your research? And I said, sure. So I have nothing to do with the books. He writes them. I just want him to put only my research in here. Well, I don't know what he's putting in here. I got to be honest with you. It could be anything. But I asked him, please stay within my research. But they're based on my papers. Let's just go with that. Now, this is electron flood theory, and this is the dipole flood theory. Now, what happens here? That's the particle being pulled out of the wave. It's being accelerated. It literally, whoops. I almost didn't get it in the right place. So what are we looking at? Let's start again. I just want to make sure I didn't leave you in a lurch here. This is the wave and the particle. So there's a particle in each one of these waves, and it is forcing all the other particles in front to get out of the way. And it's not just the particle, like I said, there's a tiny little dip. It's got a big field around it. So it's got to push everybody else out of the way. And they have fields too, because everything has they're all made out of the same particles. All right, so it's called push to shove. So this is coming through, and that's light. It should not be able to do this, according to Einstein. Once you take out the constants, it's all over. Nothing works, because it shouldn't work. It's not right. It's just wrong. So here's the particle itself, accelerating. I'm going to show you those particles in a second. And it's now gaining so much energy that it's pulling right out of the magnetism ahead, like a jet fighter breaking the speed of sound. This is breaking the speed of light. All right, it's getting ahead of the speed of light. And now it's turned into a particle. And that particle is glowing like hell right now. And right here, it separates the black from the white. As a minute ago I just showed you, these are the particles, the black and the white together. You see, well, red and black, whatever you want. But well, there's the colors are on the other side of the black. So it could be red, it could be blue, it could be green, so forth. Now, when it hit the Venturi, after accelerating, hit the Venturi, it split. And here's what it is right there. There's the black. Only the white is here. There's not a single taste of black. That is fission. This is fission. No other possible explanation for it. The black came away from the white. You don't have to be a genius to understand that. Then the white made the shower through the Venturi. The Venturi is just like a funnel, just like this. And all these fields have to make their way into that funnel. And those fields are big, and they hate each other. So when they get in here, they get violent as hell, but they squeeze through. And the black can't make it. The black has one size fits all. It never gets any different. They call it a fixed particle. Fermilab calls it a fixed particle. Never no change in particle. And it doesn't absorb, it doesn't emit, it doesn't reflect. That's dark matter. It's a muon, which is attached to the electron neutrino. Muon, neutrino, electron, neutrino. They call it a dirac. When they split, you end up with a sterile muon. All right, these are just white sterile muons and electron showers. See it? Electron neutrino, muon neutrino, stuck together. They smash into heavy water usually. The muon goes on its own way, just all by itself, and the electron turns into showers. Now, when they normally come through water, there's no barrier for the black, so the black keeps going with the white, but it sort of goes on its own. It becomes sterile. All right, here we have completely separated. So now we should be able to take that white and just squirt it right down into a battery. I mean, literally squirt it, because that's what it's doing. The bang, this is pulse. Boom, boom, boom. The black can't get through. So what is it doing? It's slapping the white. It pushes the white. It's exactly what it does. It pushes it away. So you're going to go boom, 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 and it's going to just squirt, 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 squirt. And that just pushes it down. It has no weight at all to speak of. It just goes down and fills up the battery's energy. No weight. Almost no weight whatsoever. And it's exactly what, go look up point particle from Fermi Lab. That's it. They say it's just a mathematical abstraction. There's no mass to it, and that has all the mass. I agree with that 100%. And a white can get very, very tiny. It can get very, very big. It depends on which one's pushing through. The big one charges up and flips to the back, and then they go to the upspin. So that's the downspin where the energy's down, and the next time it's going to be the upspin where the energy's up. Because they're going to flop. That's what they do. And they twist on their axis. And the red and the green are identical. They're all, and so is the blue. And it speeds up and slows down. Here's the blue slowing down. Comes through here. Very, 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 very fast. And by out here, you can see it's two particles. The blue is just ultra fast compared to the red. And green is in the middle, basically. Now, they're talking about the weight of nothing at all. Well, guess what? This is out in outer space. The Russians did this back in 2015. And this is in the space station out there that they have. And this is a vacuum chamber. Vacuum chamber was supposed to make nothing at all inside of it. Absolutely nothing. And then, apparently that's what happens in a vacuum chamber. It takes all the molecules out. Now, does that mean there's nothing in there? I don't know. But what they did was they injected these charged particles, and it made a black hole. Freaked them right out. And nobody can explain it. I know exactly, because of dipole particle flood theory. It pushes all the black to the center. The black and white can separate. I never knew it. I never ever knew it. And it doesn't on Earth. It doesn't separate because there's just too much compression. And here it's getting compressed around the excess dark matter. There seems to be an excess dark matter because when the white comes through, again, it seems to be this excess dark. Because when the white comes through here, all right, it finds some more black over here. It jumps. The black wants to jump right in. Let me show you a real close up of that, because that is the key. You see right here, when the black comes away from the white, it never wants to be away. It wants to be so tightly attached to the white, it will never try to, and it jumps right back in very, very quick. All right, that's a strong nuclear force, the black and the white. They are just tight. And the only way you can break them apart is like this, or a nuclear bomb, or something like that. And they're trying to do fission and fusion. And this is fission and that's fusion. We can do it. But we started at the subatomic level, at the sub-proton level. We started in light. They started with big balls of products, and so they're spitting off little bits and pieces. We just started with the little bits and pieces, so we're way ahead of them. And you can fit this in a little shoebox and carry it around. It should be, because this is all you're doing. It's taking the light and restricting it into a Venturi. It's going to be an angled Venturi. And then you get this effect. All right? So, and then over here, you got the condensed, really heavy-duty energy. Totally different energetic value when it's dark and when it's light. And when you see this is a nuclear explosion. And it is. It literally is a subatomic nuclear explosion. Don't forget, this is Fermi Lab, just like CERN, particle colliders. They see these, the black one, and they see the white one, red one, green one, whatever you want to call it. And they claim that exactly what I claim, that they are the black one here says, right, the summary. Extended particles have a fixed size. That's the black one. Fixed, never changes. They may have a fuzzy edge around them. Yes, they do. The point-like particles are mathematical abstractions, zero size. I don't necessarily know if it's zero, but I can't find any mass to it. It says even zero-sized particles have an extended field effect, all right, surrounding them, there's no question whatsoever. There's huge field, and it can get huge. It can get very small, and there's no mass to it, so it can squirt through that little venturi, and that one can't. It's too big. It bounces back out. But it's exactly what I say. It's exactly what I'm claiming. All right, and we can see it in our experiments. So it's not like, and there it is right there, the black and the white. That's the same particle, and of course that's the green, and the red. You saw it in the red. And actually, this is from Fermilab, but this is it right here. There's the black with the glowy edge. Exactly what they say. No question. See it? You could take that and put it right there, and it's the same thing. No difference. And the other one is the glowy one here. It gets very tiny and it gets big, but it's strictly an interaction of some kind of a springy effect. That's got me confused. How it can have so much energy and have so almost no mass at all. And here's what happens. Rod made this one come through the venturi with some black and mostly white. And see the black is pushing the white. The white is magnetic, and it makes these pulses way ahead of itself because it goes just like that. The black sweeps across because it's a fixed particle. This one is energetic, and it pushes and shoves everybody else in front, which has to push and shove everybody else. So as soon as it starts coming out, it goes, and then the black just comes behind it. And then the white, eventually, the heavy amount of white catches up and it burns the house down in the case of a nuclear blast test. And then the black comes behind it and knocks the house down. This has no mass and all energy. Very strange. Okay, this is atomcentral.com. This is a test house. The first thing you're going to see is way back up like a mile away or something, the atomic bomb's going to go off, where everything's going to get real bright. Nothing will move. It'll just get real bright. And then next thing you're going to see is the house is just going to vaporize. And that's all of these white particles just infusing into anything that's combustible. And then the black particles come. So remember, I'll show you again the wave and how it works. But here's the first part's going to come is going to be just a brilliant glow. Now I've got this running very slow motion. So all of a sudden you're going to see nothing but whiteness. See that? That's just all. Now look, that's all that's happening is the house is just fuming up. It's just not even moving. Now not only that, look back here. The wires, the poles, every single thing that has any combustive value is burning up because it's being infused with these there's no weight to them, but somehow they have all this energy. I can't figure this out at this moment. Of course, the metal tanks and so forth don't do anything because they're not combustible. They don't have any combustible products in them. But the wires, the poles, everything here, the house is just vaporizing. And eventually, well, this only is to go in a couple of seconds between the time it vaporizes and the time the house gets knocked over. So let's just keep going. Now it's basically vaporized. Now comes the shock wave. There it is. That's how an atomic bomb blast goes. Everything just vaporizes and then it gets knocked down because the black comes behind it. So what you just saw was this real brilliant glow, and all of this white stuff is burning the house, and then by the time you get to here, it's completely combusted, and all the white stuff burns everything that's possible, and then that's where the black is. The black is the thumper. It didn't move anything. It just stayed there and just vaporized. Very strange event, but appears that there's no weight to this. It's strictly some form of field, and to my mind, I have a hard time conceptualizing something that has a field but doesn't have any mass to create that field. How the hell is that happening? That's got me perplexed. I got to be honest with you. But other than that, dipole electron flood theory it solves every single thing in physics. If you can come to me with anything in physics, I will hopefully have an explanation for it, because this is quite straightforward. Everything is a dipole. 1823 make a proton, 1824 make a neutron. The numbers aren't important. It's just the fact that it's not one big mass or quarks and leptons and hadrons. Everything's made of these little dipoles. And I've shown that. I think I can't see how you can miss it. There they are right there. Those are dipoles. One up, one down. Paramagnet. And the green is exactly the same. The green, but it's much more powerful. And I can show that too. And I suppose I should. And they can see these in their particles colliders. Here it is right here. That's what we're seeing as light, because we started with light. We didn't start with all this big nonsense and smash all kinds of things all over and then dig through it. We had started with this, and then that created the colored little bits coming out of it, which is white. Actually, look at white. It changes from the color that it started, and I guess that's an extreme increase in energy, because it was red when it started. All right. Well, you know, it's hard to say. It's red. The whole thing is red. But the particle is glowing white. So I guess all particles are exactly the same. Once you tear them off of their black particle, they're just a white little particle. It's just the red's moving slow, so when it impacts with everything else, all you get is a red ripple. When you come with the green, you're hitting pretty hard, and you're getting a green ripple. But once you strip the white off of the green, it's the same white as if you stripped it off of the red, or if you stripped it off the blue, I believe. It seems to be that way. This all needs to be researched deeply, because we should be able to get free energy tomorrow. I mean, literally within days, have something like this. If it worked, the lasers are available right now. A Venturi, 15-minute to set up a Venturi. You need a collector behind it, and then you need to somehow put it into some kind of an electrical bus that just goes, because every pulse is a squirt, and all you want is the white, and that's it. That's basically the whole setup. And then you send your electricity through your motors or whatever, and to ground. The white desperately wants to get back to the black, so it will drive anything. That's what this is nothing more than electricity, and at this point it's just separated, sitting all by itself, ready to do something. And that's what it is in a battery. It's a bunch of extra white sitting there waiting to be sucked over to something, and it goes through a motor or goes through a light, through some circuitry to create light, or drive a motor, or drive whatever. That's what that does. It does work, and it has no weight. Very, very strange. Okay, I am going to let this fella talk. This is on the Sci Show, and they're talking about space and about the virtual particles that are in space. And I'm going to explain this to you. I understand them completely, and if anybody wants to discuss it with me, that's what I would like. Now listen to this.
So at any given time and place in the universe, there's a statistical possibility that there will be a little bit of energy that could just as easily disappear in the next moment. And
that is called the quantum foam.
This phenomenon has a name. They are known as vacuum fluctuations, and because this energy is carried by virtual particles, these fluctuations are often described as virtual particles instantaneously popping into and out of existence all over the universe.
Okay, let's see what Fermilab has to say about that. Okay, strangely enough, this goes back to an interaction I had with Fermilab and the Russians. Empty space isn't empty. This goes back to 2013. Look, 2013. And I was doing these light experiments at the same time, and I'm seeing the same sort of particles they're seeing with Rod Warren. And here's what they're saying. Quantum foam. What does quantum foam mean? It means empty space isn't empty. And here's exactly what they say. The foam on the head of a root beer is a complicated environment. The bubbles appear, they disappear, appear, disappear. A disappearing display of change, dizzying so fast. Empty space experiences similar activity. Subatomic particles winking in and out of existence. Why? Why would they wink in and out of existence? Are they just not there, or are they just sometimes, or are they all the time but we just don't see them until sometimes? That's what happens. We don't see them until they become hit by a photon. And I'll explain to you what I'm saying. These ephemeral subatomic particles are real and have a measurable impact on our universe. That is the quantum foam. That is precisely what they were showing here, right there. This is the quantum foam popping into and out of existence all over the universe. That's it right there. Okay, so let's go back to the SciShow. That is the quantum fluctuations, the vacuum fluctuations. See, they always thought space was a vacuum. It's absolutely, totally, 100% not a vacuum. Now watch this. I'm going to let him continue on here.
And because this energy is carried by virtual particles, these fluctuations are often described as virtual particles instantaneously popping into and out of existence all over the universe. Which means even a vacuum, which is the definition of nothing, isn't exactly empty. It's filled with an astounding number of short-lived virtual particles and the energy they carry, giving rise to what's known as vacuum energy. So we know that there...
All right, let's just see what those particles are, because I can show them to you. Okay, so this is Fermilab again, same time frame, 2013. These are the particles, the black and this is called the fixed particle, that's the point particle. The point particle has no mass whatsoever and has all the energy, and this one has all the mass and no energy. They call it fixed because it doesn't change size. And this one can get big and get small and has no mass to it to speak of. Now, this is, again, from the same people. They understand the particles, and we found those particles. And it says, in summary, the extended particle, which is the fixed one, has a fixed size. Never changes, the black one. It may have a fuzzy edge, which it does. The point-like particles are mathematical abstractions, zero size. That I can't understand, but it appears they have no mass. It says even zero-size particles have this extended field effect due to the field that surrounds them. Now, these are the two particles. We found the exact same particles. So I understand these two particles. These are the smallest particles that exist that they can find. And they say one of them just doesn't seem to ever change, and one of them just gets big and small. They attach together. It's called a Dirac neutrino. Okay, just remember this. There's a Don Lincoln again, the one who wrote all the articles for Fermilab about the particles, the point particles, and all that stuff. He's saying the neutrino is the lowest non-zero mass particle we know of. But they don't really understand it, and they don't have sensitive enough instruments to really see it or any of that stuff, really, or sense how heavy it is. But they know they exist, and they know they exist in flavors, and they can't explain that either. All right, here's the flavors. They say neutrinos don't get their flavor from how heavy they are. All right, neutrinos are going to weigh all the same weight when they're not interacting. They get their flavor is determined by how heavy their charged lepton partner is when the neutrino is created. That's true. Or when it interacts. Or from how heavy the charged lepton is that gets produced when a neutrino interacts with another particle. That's what neutrinos do. They get stronger and stronger and stronger as they build up against themselves, and then they hit the wall and then they explode. Let me show you. Okay, let's do it this way. This is the easiest way. I'll panel it out for you. Remember Don Lincoln's black and red particles. There they are right there. They're called Dirac neutrinos, and they hitch together. I'll show you in a second. And he talked about the quantum foam, which is all the light that's passing through space. And occasionally they hit each other and they glow for a second and they're gone. That's the quantum foam. He talks about the standard model being the most perfect model there is. No, it doesn't work whatsoever. It's completely wrong. Protons are not made out of a couple of little particles. They're made out of all dipole electronics. All right, dipole electrons, which are these particles right here. These two, black and white together. They will always be a black and a white together. And when there's two of them back to back, that's a photon. When they're just half, it's called a gluon. And then the black can separate from the white. Shown it all. They have seen this. They just don't understand where it came from. They just say, wow, look at that. These are the tiniest things we can see. This has no mass. As I showed you from Don Lincoln's article, this has no mass, and that has all the mass. And it has a glowy edge around it. And if you can't see the glowy edge around there, I don't know what to say. And that's black. It never changes. And I can prove that too. These can get big and small. That's small, that's big. That's big because it's concussing with all the particles that are in front of it that it has to push through. It builds a field. When they compress a field against a field, it gets excited. And I'm sort of having a hard time understanding this because there's virtually no mass to that. As I showed when the house doesn't move, all it did was burn. This stuff was away from the black at that point. So all we had was this down here. Normally the black and the white is attached, but when the bomb goes off, the white goes way out fast first. Then the black sweeps across, as I showed, and I have another photograph that shows that. Now, don't forget, we're talking about the neutrinos. A muon, neutrino. Electron, neutrino. Smallest particles that exist. Attached together, they make a diarac, two particles, diarac, neutrino. When it breaks, the muon goes sterile. As you see, the black particle goes by itself. The white goes into shower mode. There's no question that happened. Now, how do you make that happen? You have to accelerate the light. How can you accelerate the light? They have no idea how to do this. They've been trying to figure this out since 1978. They had a big special meeting on how to do photon collisions. Now, I'm working with another guy in Italy right now, Rocco, who is getting deeply invested into this, and I'm hopeful that he can carry this on. I'm about towards the end of my realm on this, but he went out and got the same equipment we have. Rod Warren and I had it's incredible. But this in 2014, we were doing all of this stuff with a Galaxy Samsung S3 phone. That's all that was used to do this. And the reason it works so well is it's CMOS. And what does CMOS mean? Complementary metal oxide silicates. I had some guy the other say, CMOS? You're using a moss out of the sea? I said, no. CMOS is a metal that absorbs electrons. So when it gets hit with radiation, it turns on the little pixels. And somehow they did such a fabulous job on that specific phone. And all they're using is the selfie side. This is the as this light is coming through the Venturi. It's absolutely phenomenal. And it's almost very low cost. They're hitting things head on. So what they're doing, well, let me show you. I can show you their own. These are their own pictures. All this stuff was right from Fermilab. I didn't do any of this stuff here. That's Fermilab, 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 the Diracs, Fermilab. This is Fermilab quantum foam and quantum waves. Well, yeah, we can see those. I can show you those in reality, not just pictures. There's the quantum waves out there. You have to do a little, they got to come up to speed here, I'm telling you right now. Look at this. Look at this. This is what's out in space. You think particles aren't getting influenced by all this stuff? There's more dust in space than there is in my living room. Well, maybe not. All right, just think about this. This is a proton, and here's a neutron. What's the difference? A proton has 1,823 particles, and they become stable at that point, semi-stable. Because it's an odd number, it wants to take one on or give one up to become neutral. Neutral just means a zone of stability that doesn't want to give one up or take one on. A proton is different. A proton is a charged particle. It wants to either give one up or take one on to become like a neutron. So, but what they're using is huge particles. This is what they're actually made of inside. They're all of these tiny little particles. And they're dipoles, just like I showed you. And I showed you in the pictures, there's no question that's what they are. And that's what light is made of. Now, what they're doing is going, bam! And then all of this stuff goes flying everywhere. Now, what is flying? What do we see flying out of there? Well, we see light particles right there. These are photons. I showed you the photons. All right, these are the photons. Right there. There's the photons. I see photons. That's exactly what came out of that head-on collision of their giant particles. So they see some of these, and then they'll also see these here, which is the little black balls. They actually don't see the black balls because all they can see is the things that illuminate because of the instruments they were using. All right, we can see the black balls because they lay on top of the white. That's the only reason you can see them. You can't see them over here. They're in there. They're all over the place. They're everywhere. They're everywhere. You don't see them. The only reason you can see them, you don't see them over here. No black balls anywhere. The only black balls you see are laying right on top of the white. So they're obscuring us from seeing the glow of the white. Normally, there is always going to have a surrounding of white particles around the black core. The black core will never come out of there until you do the atomic bomb thing, where all of the white particles go out instantly. And then the black particles, the heavy-duty ones, they come afterwards. And that's this effect right here. Wait a second, where is it? Hold on a second. All right, so where are we? That's the Venturi. The pulse laser's coming through here, through the Venturi, and now it's spreading back out again. This time, instead of only the white, we have some black coming with it. So it depends on how wide the Venturi is and the construction of it. Rod was exceptional, absolutely exceptional. He did all this stuff. I'm not taking credit for this. I'm taking credit for understanding what the atomic nature of it is. He's one that did all the physical labor here. I can't take any credit for that whatsoever. And he created the Venturi by accident, which was literally 2 nails, just like this. And this is exactly what he did use. Just like that. That same laser, 2 construction nails, which were just little finishing nails, and this exact same phone, Samsung Galaxy S3. And he used the selfie side, and he took pictures all around here as these events were occurring. And there's something about this phone. I don't know what it is, but I'm going to tell you what. There's something about it. It's got to do with the CMOS and the pixels and the density of the pixelation and the CMOS, efficiency. Let's put it that way. So coming through, instead of just the white, we got black and white. Remember, we had just white coming here. You see? The light accelerated. There's the particle. The black separates only the white. Only the white goes through there. No black whatsoever. And that means what we did, whoops, that's the wrong one. What we did was we created fission here, which means we separated the black from the white. That's what fission is. And this is the smallest place you can be at in fission. You can break this apart. That's fission. That's fission. But once you get down to one of these, which is the last bit and piece there is, and you break that apart, that is really fission. Now we're talking fission. And there it is right there. The other things are just pieces broken apart. This is fission of the subnuclear particles. Now, only the white went through here. And that white is the only thing whatsoever that is electricity. This is electricity. And if we can just harvest that separated white while it's separated, and we didn't do anything to separate it, we just forced it to go through and not allow the black to go with it. And then once it comes through that Venturi, if we could put a harvester right there, which is this little thing I drew up years ago, and I can't see why nobody will talk to me about it. The laser shoots the black and the white particles. The black can't get through. Now, we don't care about the black. The black doesn't burn anything up. It doesn't do anything other than attract the white. We don't want the black, so we keep it out, no problem. Exactly what we did. So now what do we have? Raw white. And the white has no mass to it. So it's just, this is slapping it. As we can see, the black pushes the white, and I'll show you that one more time so there's no question about it. So we have a wave of black bam, bam, and it's pulsating. Bam, 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 bam. And what does it do? It squirts the white. Squirts it. And I can't see why we can't squirt it down into a battery. With a photodiode, it means it goes one direction, can't come back. There's a gate on here, so it goes through the gate, and it's in there. It's in your batteries. When it tries to go back up, the gate closes. Nope, can't go back. It's boom, 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 boom. And the amount of energy should be staggering. They say it's in the trillions of electron volts. If you can separate these two apart, you can get trillions. That's called electron showers. And you can get trillions of electron volts. And they are electron showers, there's no question. And here it is right here, it says it. Electron neutrino turns into electron showers. There it is. Why can't we do this and get some free energy and have somebody talk to a Roger about it? Because this is the same particles as Fermilab shows. Right? And like I say, I engaged with Don Lincoln, but it didn't go all that well. Now, they know that the standard model doesn't work now. I mean, there's no question about it. They just don't know how to handle it. And they keep saying different particle names, axions, and all these kind of crazy things. Well, it's a very simple particle thing now. It's just one particle. All right? This is what a gluon looks like. Two gluons together is a photon. We can do all kinds of destruction of this, and we can also see the neutrinos building their energy as they move forward. You see that? That's a neutrino. It's not a photon yet. This is a neutrino too. It's sideways. This one's flat. This one goes sideways, and then they turn into photons. And the only reason they're getting glowy here is because they're going to hit the Venturi right here. This is the single line of glowiness. You just don't see them up here. This is an area of concussion now, so they're pushing back. That's the only reason you see them up here. All right. This is the line of acceleration. You see? Remember? There it is right there. Now you can see these back here glowing now because of the energy coming back at them, but not coming this way. You don't see anything up here, nothing up here. It's only because it's coming backwards from that literally subatomic nuclear explosion, where that's what happens in fission and fusion. That's it. That is it right there, my friends. And it explains literally everything that's going on in the universe. It explains why light is slowing down, coming towards us. This universe is filled with these particles. Every time something emits light, those particles are out there. And they are particles. And these are the particles right here. And that's what they look like as light. Okay, let me go up a few last things. This was done in space in 2015 by the Russians. And this was in a vacuum chamber, supposed to be no particles whatsoever. All the dark matter went to the center. The charged particles came around the outside. It freaked them out. They said during the experiment, we contacted the Earth guys who couldn't believe it either. Nobody was expecting this. Now, electron flood theory does explain this perfectly well. The white particles can separate from the black. I never thought it was possible either. But once you get from the restriction of the crushingness of Earth's gravity, they can separate into this. Now, the only reason that this is not perfectly round is because it's still out in the gravitational influence of Earth, so it's still coming down. But the white is crusting around the black. This is what they never understood. So whenever you look at anything, all you see is the white. The reason you're not seeing any white coming right here is they're shining light into it to see this. They're illuminating these particles that are inside. And this does not reflect, it does not absorb, and it does not emit. So you get nothing there. They're shining the light. You can see all these other particles out here, but not here. All right, I hope you understand that. So the center of all things is dark matter. And when you shine light on dark matter, nothing bounces back. That's the nature of dark matter. Okay, these are what they consider to be Higgs bosons. They know they're little spinny, circling-looking things, but these are just drawings. Now let me show you the actual Higgs bosons, and they are created when the black and the white particles come back together. All right, here's what I want you to think about. If we shine the camera into here, the white, we're going to see nothing whatsoever. But around the edges, we're going to see all these Higgs fields, because they're trying to grab a hold of the white. That's what happens after it comes through the Venturi. So here we are, right there, taking a look to see what's coming out of the Venturi. And here is what is coming out of the Venturi. All right, this is just one shot. This is coming out of the Venturi, and these fields are just flowing out of there as the white reattaches with the black. All right, so here we are with, right here, taking the picture. We're in the white, so we're not going to see anything right here, because we're not yet back to where they're attached. But they're trying to come in from the sides, so we're seeing them come in around the edges. Now, eventually, they'll all be Higgs fields out here. And these are the fields. Now, if you look at where the white spits are going, they're hitting the edge of these fields, and they're just spinning like crazy because they're banging into a black particle. And then they start to make their tumble. All right, remember we separated the white from the black. Right here, they're starting to reattach to the black. Every one of these is going to be one of these little dipole particles. And you see the little whites, and they just start to sizzle and they have to find a partner. And when they do, they just start spinning like crazy. Now here's a real close-up shot. And these fields are impinging on another field, and it turned it blue, which it's all coming through red, and it's supposed to stay red. But here's something else I noticed, really interesting. You see these little circles right in the center? I'm wondering if that's where the particles is spinning itself in the center, causing the field to create around itself. Originally, I thought, well, I really don't know what I thought. I knew that it was spinning. I thought the black and the white was just, but no, it can't be. It has to be a field surrounding, just like the fields that surround planets and so forth. All right, these fields, look at this. These are fields that surround spinning particles. Planets are spinning. Now the moon is not spinning, so it really doesn't have a field. I don't believe any field around the moon. Here's the moon. You don't see any field that's making. Something else behind the moon is creating this magnetic fields. There's some strange stuff going on out there. But everything is dipole. See the black and white, black and white, black and white, black and white, black and white. Now the blue and the orange, I think I understand that, and that's the crushing of the particles as the moon is just being dragged around. It's not spinning like we are. Or basically everything in space is spinning unless it's attached as a orbital object, as our moon is. I believe that's what it looks like to me. And again, we can see the green. You see how powerful that green is? The same particles, same exact particles as the red, but much more powerful, and I can show them at the same time. Here we are coming through the Venturi at the same time. The red just gets pushed out of the way, very weak. The green concusses with the red and then reconcusses out here because it's just much more powerful. And then the blue is just rocket ship. And here's the blue coming in fast, slowing down. And by the time it gets out here, you can see there's two particles. Over here, it just looks like there's one, but it's not. It has to slow down. Blue is just too hard to work with. It's just too fast. But the red, you can see very easily. You can see the red particles gaining their neutrino values, turning into photons, and exploding. Each one of these is a wave, and the dark part is in between each wave. All right, that's just the way it works. Just like here, you see the wave and the dark and the wave and the dark. And that's what happens is because it's push to shove, push to shove, push to shove, and there's always going to be a space in between. If you look up Kashmir effect, you'll see this. Now, I know I'm dragging this out forever, but all I want you to understand is, the only thing that exists is this one here, the white one and the black one, a W and a Z boson. That's it, case closed. Everything else is made out of those two particles. Everything else. Those two, when they jump back together, they create the Higgs. It's not the Higgs creates them. These two joining create a Higgs. And that's after its energetic value it jumps back together. Once they're really growing, they're apart. When they come back together, they're a Higgs, which is the most stable of these tiny particles, basically, as far as I can tell, which is the glue. The two of them together make the Higgs. I say the Higgs is a gluon, because it's these two together make the gluon. The Higgs is made out of those two, so the Higgs is also a gluon. A photon is two gluons together, and that's it. From up there, then you start adding more and more and more, and then you get to zones of stability. And 18, 24, or 25, 26, something like that, 18 somewhere, is what hydrogen is going to be made out of, is that many particles. It's not just one big proton and an electron. And then you get up to helium. Now you're way up at 7,325, I think, something like that I calculated on. And then you start getting up, the number of quantity of particles up in here is just staggering. They're not just 25 or 26 or 50 or 55. They're hundreds of thousands as you get up high enough, because they have a ton of neutrons as well as the protons. That's why you can have so many isotopes and still be the same, like carbon. Carbon's all kinds of things. Carbon can be way up this side, way down outside, but in the middle, there's a zone that's stable. All right, this is the easiest way for you to visualize it. That's carbon. But guess what? I can take these many away, it's still carbon. I can take these many more away, and it's still carbon. This many more away, it's still carbon. I could add, on top of the stable state, I can add more and more and more and more. And then at some point, it becomes so unstable, it just can't hold on anymore at all. All right, those other isotopes have what they call half-life. So if I threw a whole bunch more on there, it would stick to there, and it would be okay for an instant, but then it would decay back to stability. That's what isotopes are. But we know that there is a million, zillion different little particles between each one of these. So it's not just one chunk and that's it, and the next chunk is one bigger. No, it's one, and then there's 1,000 different little pieces, and then we call it the next thing. So from carbon to nitrogen, you could have, there's probably thousands of particles in between, just in between those two. And when you get up into here, there's tens of thousands between each particle. And that allows for enzymes to come in and break these apart to create life. These just particles would never make life work. All right, so I know I'm going on a couple of different zingers here, but this is what everything's made out of, and life is made out of it too. Light is made out of it. These two are the light particles. Everything that's made is made out of it. Protons make up everything there is. Protons, neutrons, electrons, they have little gluey spots on the outside because they're magnetic. Everything's magnetic. That's all there is. All right, so don't forget, electron flood theory is the key. We found the particles. They're out, and there's no question whatsoever, they're the exact same particles, and they come in red, blue, green, and probably a variety of other colors. We were working with lasers that emitted these specific colors. We can see that we could separate the white from the red. That's fission, and then when it comes back together right here, that's fusion. We created the Higgs fields, and we can do this continuously and run this without stopping. And I don't see any reason we can't harvest that energy before it hits here, because it desperately wants to be attached to this. But we can harvest that and bring it down into a battery stack. Then we can let it come back to these eventually after it goes through motors or whatever we want to run with it. That's the key. All right, and like I say, all of this stuff makes sense when you start to go into electron flood theory. And even why galaxies spin like this, because they're spinning and there's all particles in space in front of it. So it pushes the arms of the galaxies back. And then there's always a dark and a light spot in between. Dark and light, dark and light, dark and light. Because the push to shove, push to shove, push to shove creates these, what they call interference patterns. And as they keep going this way, they keep forcing matter closer and closer, just like a wrench. And it gets tighter and tighter in here. And that's where your dark matter is going to be, deep inside there, because the dark matter is what collects all this stuff. As I showed you in the Russian experiment out in space, the dark matter itself will pull more and more light. The more and more dark you have, the more and more light's going to come in. And that's why you get these supermassive black holes. And that's why they all spin in space, because there's so much debris in space and so much energy that as they move through space, and it seems to be everything is spinning. Right? So if it's spinning, its particles that are wrapped around it have to push against the particles in space, so they did this, and then they fold back. And then you get these patterns. Now, if we are in a zone that's very void of extra particles, we're not going to overheat a whole lot. If we're in a real dense spot, or come into a dense spot, that could be what's affecting our atmosphere, but it is not. What is affecting our atmosphere is we're blowing it up like a balloon. All right, it's because of the greenhouse gases. They're right about that, no question whatsoever. Our gases envelope is going, and then it scrubs harder and harder and harder through space. That's what way out in the ionosphere, where it's scrubbing through space as we spin. It's thousands of degrees. I think it's 2,700 degrees out there, something like that. Why is it so hot out there? And the sun, and the corona of the sun, is millions of degrees and only 10,000 on the surface. They have no explanation for this because they don't understand any of this. It's really kind of disheartening that as I approached Fermilab, showing the same particles that they have, I wasn't making anything up. I was showing these same particles right here and showing the same characteristics of these particles and showing them separating, fission and fusion. And I was told I was a tinfoil hat guy and stay away. Don't ever contact us again. That was 8 years ago. And nothing has changed since. And I went to the University of Geneva for particle physics. I showed them all my stuff, and guess what they did? I don't know if I had anything to do with it, but I showed them, and I said, we accelerated the light. We used a Venturi to do that. You have to focus. They were just trying to let things hit by accident, coming around and banging this way and that way. You got to focus them in, like head on, obviously. I said, we don't have to focus. We crushed. Same thing. You're hitting head on is crushing. You're hitting sideways is crushing. Doesn't matter. But we can do this and focus it all day long. And I showed them, and then when I told them we did it with almost no expense, there was didn't seem to be a whole lot of more interest. But I did notice about a year later they shut down CERN, and they put in focusing magnets to focus, and they put in CMOS as a detector. Because at first they said, you can't see all that. So I said, yes, we can see it using CMOS. And he said, no, that's impossible. I said, no, it isn't. Here it is right here. And then I did show it to them. I showed them everything. And then they just said, that's interesting. And that was it. And then they shut down CERN. CERN's back up online. It took 3 years to upgrade the magnets and the CMOS and do all the other things they did. And it came back online, and now they're getting much better results, obviously. But still, all they're seeing is debris. This is what they see. Where is it? This is what they see. What are you going to make out of that? I know the different colors. I know why there's different colors, and I know why the red doesn't go out like the blue and the green and the yellow go flying and never come back. The red sort of just hangs around. It's because of how glued they are to the central core. The blue ones are so glued, when they go, that's it. You have to knock them so hard they never come back. Same thing with the green, but when you get down to the red, they're just sort of flopping around anyway. That's the way outside stuff. So they just sort of bounce and come back. All right, but we don't have to do that because we were just working with the tiniest of particles. They could never get down to that realm. And they don't want to get down to that realm because it changes. Do you know how many trillions of dollars is spent every year around the world trying to look for these particles that we found for virtually nothing? That's the problem. Too efficient. All right, my friends, that seems to be the way of the world. The more complicated you can make it, the more money you can take in. And that seems to be the whole motivation now. But I'm going to tell you right now, our Earth is in so desperate of trouble. And the places where they're pumping oil, like Russia, they're just destroying their countries. And we are too. And the land, the water, the whole thing. But I guess that's what's going to happen because they don't want to get down to a point where anything can be basically free. But this would set us free if we could get free energy and everybody could have access to it, because that's the whole key. That's the whole key. As far as I'm concerned, maybe I'm wrong, maybe I'm right, but I don't think we'll ever find out. All right, I love you all. Don't forget, electron flood theory. Everything is made of dipoles. There's a black and a white to everything. All right? Two of them together make a photon. All right, that's my last word. I love you all. Thank you. Don't forget, electron flood theories, dipole electron flood. This was back a paper I wrote back in 2019, but I had this for years. I knew about dipoles. I called it light is atomic vapor. Atomic vapor. What's the atomic vapor? It's a positive and negative particles, and they come out just like moisture in the air. And then when they congeal together, they turn into rain or ice or whatever. But these turn into matter. And they only get stable at certain quantities. These little tiny things make up zillions and zillions of these. And at certain quantities, they become elements, atoms. But in between each atom, there's a million, well, you know what I mean, there's thousands sometimes of other particles that are almost there, but not quite. And they're not stable. They won't stay there. But they are needed to react in chemistry of enzymes. When an enzyme creates food in your body and different molecules and so forth, proteins, it has to be able to break and make things instantly. And they do hundreds of thousands of reactions per second. One enzyme, and it's just stunning. I know this is probably getting a little confusing by now, but if you haven't seen what I showed you about particles, well, I don't know what else I can say. But you have to go from there into life. Well, how do these particles turn into life? How do they become alive? Or are they alive when they started? There's a lot more to this than just what I'm showing you here today. Nothing ever ends. There is no end to anything. If you start looking, you're going to have to keep looking. Otherwise, you just give up. I'm not a good giver-upper. So I'm going to just keep doing what I'm doing. And I'm going to be finding all this stuff and speaking about it. All right? So I love you all. Thank you. I know it's been long, but that's the way it's going to have to go. Okay, let me just read you this. This is about the discovery of the Higgs boson. And this is the Nobel Committee, the Nobel Prize gave them an award for this when they discovered it at Atlas and CERN and the Large Hadron Collider. Now, the discovery of the Higgs boson may have completed the Standard Model, which it did not. But this wasn't the end of the investigation of this elusive particle. One of the major discoveries in 2012. Okay, this is about the Nobel Committee giving them an award for finding the subatomic particle that we're talking about, which is the Higgs boson. Discovered the Higgs boson. Now, it says the investigation of this elusive particle. Okay, let me just explain it to you. This is the Nobel Committee giving CERN a Nobel Prize or somebody for discovering this subatomic particle, which is the Higgs boson. Now, this literally is the tiniest particle that exists that is semi-stable. It's one black one and one white one stuck together. It's a Dirac neutrino, really. But they see it when it's spinning. All right, and I'll show you what it is. Now, it says the investigation of this elusive particle, because they only see them when they spin, because they're seeing when they explode. Now, the investigation of this elusive particle will deepen during run 3 of LHC, Large Hadron Collider, particularly when the particle accelerator's high luminosity, which is what we use, upgrade is complete in 2029. So they're doing an upgrade to get, and they already did an upgrade in 2017. Now, this will allow the LHC to conduct more collisions, providing researchers more opportunities to spot exotic physics including phenomena beyond the standard model. I've shown you exactly what everything consists of. So there is no more physics to discuss except for to investigate what I say and then say, no, Roger, you're wrong. But that can't happen because I, Roger, am right. Now, the CERN estimates the following upgrade each year. The accelerator will create 15 millions of these particles. 15 million, we create that in 10 seconds. This is compared to 3 million Higgs bosons created by the LHC in 2017. And that's when I was going to University of Geneva. And I showed them all this stuff. Then they shut down for 3 years to upgrade to exactly what I said. Now, I don't know if it had any influence or not, but they went into focusing and they went into CMOS to be able to see. Instead of charge coupled devices which work, they either send energy in or they extract energy out. All we're doing is waiting for the energy that's going to be emitted to hit us. That's what CMOS does. And they realized it and they said, ooh, that makes sense. Now, listen to this. It estimates the following upgrade, which will create 15 million of these particles in a whole year, and compared to 3 million created by the LHC in 2017. This may be key to detecting other flavors of the Higgs boson. I showed you flavors of the neutrinos. Can I show you flavors of the Higgs boson? Absolutely. Okay, so what is CERN and all the rest of them doing? They're sending these particles around, and then the two of them, sooner or later, will hit head on. Very rare, though. When they do, they spray particles everywhere. And they see these spinning little fields. They call them Higgs fields, Higgs bosons, Higgs fields. And that's exactly what I showed you in our experiments, only we didn't use head-on collisions. We forced our stuff to create these fields going through a Venturi. It crushed the fields exactly the same as crushing them head-on. No difference whatsoever, except we made them go through and they crushed each other sideways. They didn't have to hit head-on, but they did hit and they split and they did make all of these exact same patterns. All right, don't forget that's light just starting to accelerate. That's why you're seeing all this glow. Otherwise, you wouldn't see anything there. You'd just see maybe a little bit of glow, but you wouldn't see these fields. And so it's starting to accelerate, and now it's in full acceleration mode. And there's the particle itself being ripped out of the magnetic field, just like a jet fighter going through, breaking a sound barrier. This is breaking the speed of light. And here it does explode, and we can see all the particles at that point, and then is where we see all the Higgs fields come over here, because that's when the particles come back together. So that was this, that's accelerated, and when they come back together, coming out of here, they bang into other black particles and turn into the Higgs fields. It's exactly what's going on. Now, can I show you flavors of Higgs fields? Yes, I can. So here we have the red Higgs fields. Okay, these are other flavors. These two are other flavors, but they're only flavors because they're being pinched. So you can get a Higgs field out here and crush it, and it will change into a different flavor. And that's why it looks different too. The structure of it. That's the same particles coming out. They're all the same, but this one got pinched between two other fields, and I think I got a better shot of that. And that one right there, my friends, is the one that really stunned me. That is a reverse spinner. All right, let me bring this in a little bit. All right, what do we have here? We have particles coming out at us. And there's just white here. There's just white. But there's some kind of particle there, because you see the little spritz? There's got to be a particle. All right? They say there's no mass to it, but there's got to be something, because you're seeing it bang into these and start spinning. All right, they're coming along and they're banging into somebody and making that thing spin. So it's hitting a black particle and making it spin. So this is coming out at us. And we are inside the white right here taking that picture. Now, they are all spinning in one direction. They're supposed to spin right hand, they say. That one is spinning left, apparently. Now, what does that mean? Instead of its field being thrown outwards, its field is being brought inwards. That's what my take of it is. That's all I can take from it. So instead of spinning outwards and creating these outwards spinning fields, it's spinning inwards and magnifying its field inside instead of outside. That's all I can take from it. And then let me show you what I think happened with that particle. Okay, don't forget I showed you the flavors of neutrinos. That's a neutrino. That's a neutrino. These are photons. And the green is the same. Here's the green right here. That's a neutrino. These are neutrinos until they hit the photon stage. The green is exactly the same as the red. Identical, no difference whatsoever, only it's spinning much faster and harder. But it's the same particle. It just spins faster. And that's why I can show that too, coming through the Venturi at the same time. We see the green go way out here, red just here. And it's strictly because of how fast it's spinning. And it's all about the spin. And the blue is just rocket ship fast. You can't deal with it. It's just too fast a spinner. Now, can I show you the flavors of the Higgs? Yes. I showed you the flavors of the neutrinos. Well, here's the flavors of the Higgs. Don't forget, there's the flavor of the red flavor, and here's the green flavor. See? Now, what did we do here? We did the same thing as with the red. We separated the black particles. You see that black one's coming all over here? And there's none here, not a single one, zero. I looked at it very carefully. There's none out in this area whatsoever. And I believe the Venturi was a little offset, so they sort of banged away and caromed off this way, and none came this way. But it obviously shows you these are the Higgs fields with the green, which is that's much more powerful, much more powerful. You see this? Theories that go beyond the Standard Model also predict as many as 5 different types of Higgs bosons, which may be produced more infrequently than the primary Higgs. Their primary Higgs is the red one, because that's the easy one to see. And I can show you that right here. You see this? This is what they see, is this kind of nonsense. All right, the primary Higgs is the red one, because that's the cheap one. It just hangs around. The other ones, they take off. You're never going to see them hardly. We had a hard time seeing them, even with the green. You can't see them with the blue. Well, maybe you can, but we can't. The green, I could see them right here. There they are, right there. They're Higgs, but they're not so exquisitely visible as the red. The red is just absolutely flawless. I mean, look, this is Higgs on the move, I call this, coming at us. You see him? Then you got Higgs here. We're in the midst, well, we're at the end of the Higgs coming in. Well, this is the white showers, electron showers. Now they're hitting and they're creating their own Higgs. Now, we could, if they want to find so many of these Higgs in a year, 25 million or something, we could do that in 10 seconds. Literally 10 seconds, you could create easily 25 million Higgs. And all I can say is this changes everything, but it has to be examined. All right, I'm going to leave it at that. Thank you all for paying attention. But don't forget, we found these same particles. These are the same particles they found 10 years ago. We found them as well and have been not denied to have anybody look at it. So it's never been examined since initial discovery.